two charges Q1 and Q2 of magnitudes positive 4 microcoulomb and 3 microcoulomb, the sign is unknown, respectively, are placed in a vacuum as shown in the diagram below. P is the point at the distance r to the right of Q1 and 0.2 meter to the left of Q2. The net electric field at the point P is equal to 0. So 8.1, are the signs of the two charges similar or opposite? Give the reason for your answer. So here, for the signs to be let's say similar, if the signs are similar, it means that, or let's say the net electric field is 0. It means that the electric fields, or the two electric fields of these two charges, are going in the opposite directions. So once they are going in the opposite directions, it means that the net electric field is going to be 0. But if they are going in the same direction, we add up. So the net electric field will never be 0. So it means that the signs of these two charges are the same, because this one is going to push P to the left, this one is going to push P to the right. That's why at the end the net electric field is 0. So now we're going to say 8.1, the signs, they have the same, let's say they have the same sign. Why? So we're going to say for the net electric field to be 0, for the electric field to be 0 at point, for the electric field to be 0 at point P. So since we're talking about point P, the two, let's say the two electric fields must be in the opposite direction. So for the net electric field to be 0 at point P, it means that the electric field of these two charges must be in the opposite direction, so that when they're in the opposite direction, we subtract the other one on the other, so the answer is going to give us 0. Because the other one's positive, the other one is negative, right? So 8.2, draw the electric field pattern around the positive point charge. So the positive point charge, this is the positive point charge. So remember, on the positive point charge, the electric field lines, they point outside. They must point outside. So this is what we wanna see. So the electric field line, they point outside, so we can extend, no problem. So make sure all of them, they point outside. So this is the positive charge. So if it was a negative charge, it means that the electric field lines, they must point inside the charge. So now 8.3, let's just divide. 8.3, they said define electric field at a point in width. So electric field at a point is the electrostatic force. Or first we can just write the formula to see what's going on. So this is the formula for electric field at a point. This division. So electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. So we can say is the electrostatic force experienced per unit positive charge, per unit positive charge placed at that point. So this is our electric field at a point. The electrostatic force is the electrostatic force experienced per unit positive charge placed at that point, right? So now 8.4, for 8.4 can just open a new page. So 8.4, you calculate the distance in meters. So that means the distance r in meters. So they're talking about this r. So for us to calculate this r, the definition, it was talking about the electric field. So it means that we must apply the electric field, not not a Coulomb's law. So it means that we are given the net electric field, net. So at the end we must include the net. So let's say now we start by calculating the electric field at P due to Q1. So let's say now we write down the formula. E is equals to KQ over R squared. So remember, for electric field we only have one charge here, not two. So now electric field due to charge 1, let's just say 1 for charge 1, is equals to K is 9 times 10 to the power 9 Coulombs constant. Then the charge here is 4, but since it's a micro, so we're going to say it's 4 times 10 to the power negative 6 for microcoulomb, remember? So what is the distance? The distance is r squared. So here we're going to have this one times this one. It's going to give us 36,000 divide r squared. So we can say this one, let's say this one is our electric field at the P due to Q1. So now let's say we are looking for the electric field due to Q2 at point P. So let's just write 2, and then K Q1, or let's say Q2 over R squared. So our K is 9 times 10 to the power 9, and then the charge here is 3 now. So it's 3 times 10 to the power negative 6 is micro. And then now what is the distance? The distance is 0,2. So this is going to be 0,2 all squared. So now this one, when you punch the calculator up there, it's going to give us 27,000 divide. So this one is going to give us 0,04. So 27,000 divided by 0,04, the answer is going to be 675,000. So this is the electric field at the point P due to Q2, right? So we can do this before we go far. Let's check. Since we said these two, they have the same sign, and one of them already, Q1, they said is positive. It means that even Q2 is positive, right? So when we draw the vector diagram, let's say let's draw the vector diagram here. So Q1, since this is a point charge is always positive, right? So it means that the Q1 is going to push P to that direction. So this is Q1 pushing P to that direction. So this is the electric field Q1 on P. So this one now is going to push P to the left. So this is the electric field. This is the electric field Q2 on P. So it means that the electric field Q1 is going where? Is going to the right. So we can just say this is right. And then this one, 2, is going to the left. So we can say this one is left, to simplify life. So since now we have the electric field due to Q1, electric field due to Q2, now we must calculate the distance R that they're talking about. So since we are given the net electric field as 0, so now we're going to say E net as the electric field, or the net electric field, is equals to, we have the electric field 1, or charge 1 on P, plus, since it's a net, that means we are adding here. Since, let's check, 1 is going to the right, 2 is going to the left. So if we choose right as positive, it means that the other one is going to be negative. So let's say negative E2. So now the E net, they said the net electric field at point P is 0. So it means that here we have 0 is equals to E1 minus E2. So to simplify life, let's take E2 to the other side. It means that now we're going to have E1 is equals to E2. So now, what is E1? Let's move this. What is E1? E1 is 36,000 divided by R squared. So now we're going to say this is 36,000, we divide by R squared. That's equals to, what is E2? E2 is 675,000. So this is 675,000. Then this is out of over 1. So we cross multiply now. So we're going to have 675,000 multiplied by R squared is equals to 36,000. And then let's simplify life. We divide by the coefficient of R, which is 675,000, both sides, Jesus rule. So this one cancel this one. So R squared is equals to 36,000 divide 675,000. So let's just take the square root here and simplify life. So it means that now, therefore, R now is equals to, R now is equal to 0.23 meters. So this is distance R according to the information given.